In this video, we're going to learn about eigenvalues and eigenvectors. Before we get on to what those are, let's just explore this matrix here and apply this matrix to a few different vectors. That is sort of transforming a point in 2D space. So if I do that, I can use this little trick to apply this to all four of these in one go by applying it to this sort of stacked 4x2 matrix. So I'll just load them all up here and apply the matrix one at a time to each one and see what I get. So applied to 1, 4, I get 2 times 1 plus 5 times 4. So that's 2 plus 20 is 22, minus 1 minus 16. Okay, so that's minus 17. So nothing particularly interesting there. How about to the 0.22? So that's 2 times 2, so 4 plus 10. So that one's going to 14, and the next one, minus 2 minus 8. Again, nothing particularly interesting there. What about 1 minus 1? Well, I get 2 minus 5, so that's minus 3. And then minus 1 plus 4, that's 3. Something interesting happened there. The relationship between the original position 1 and minus 1 is the same as the relationship between minus 3 and 3 in the sense that the y value is just the negative of the x value. And what about this last one? Okay, 2 times minus 5, so it's minus 10 plus 5, that's minus 5, and 5 and minus 4 is 1. Well, that one didn't change at all. So what we can see is that for a given matrix, there are going to be some vectors that get fundamentally changed. So what do I mean by this? I mean, if I started with the point 1, 4 and the vector connected to it, when I apply this matrix transformation, this gets taken to the point 22 minus 17. That's way down here in a completely different place. Similarly, 2, 2 gets mapped to the point 14 minus 10. Again, miles away. However, the point 1 minus 1 gets mapped to the point minus 3, 3. Now that's interesting because that's on the same line. Right, it's on the same line that it was on before. And what about this last one, this point minus 5, 1? I'm just doing these very roughly. Well, that one stayed the same. So that's also on the same line as it was before. Now, these sorts of vectors are special. If you apply a matrix to a vector and it just scales the vector, it doesn't actually move it, so it scales it to another point on the same line through the origin, that vector is called an eigenvector, and they have lots of very special properties. Now, if you've learned about invariant lines before, this is a similar concept. An invariant line is one that just gets mapped to itself. So an invariant line is one that contains all of the eigenvectors. Okay, there are some matrices like this where we could probably predict what the eigenvectors are going to be by considering what the matrix actually does. This matrix here, in case you haven't spotted it already, this is a reflection in the line y equals x. So you might be able to think already, well, which vectors or which lines through the origin are unaffected by this, or at least are mapped themselves? Well, it's going to be just the sort of line y equals x. So certainly the vector 1, 1, or 2, 2, or minus 1, minus 1. This should remain the same, and we can check that it does. And that makes it an eigenvector for this matrix. So 1, 1, we apply this and we get 0 plus 1 and 1 plus 0. But the point minus 1, 1 is also going to be, well, it's not unaffected, but it is just going to be scaled. Look what happens. If we have minus 1, 1, that gets mapped to 1 minus 1. So the vector that we get out is just a multiple of the vector we put in. So every every matrix that has one of these or some of these eigenvectors obviously has infinitely many, because if 1, 1 is an eigenvector, then 2, 2 is an eigenvector. So really we're thinking about families of eigenvectors. So here's a little definition. Suppose we take some vector m and we apply it to some vector e. We don't normally call vectors e, but it's e for eigen. So I apply it to some vector e. If what I get out is simply a scaled version of e, so that is lambda e, then we can say that e is an eigenvector and it has a corresponding eigenvalue lambda. So in this instance, 1, 1 was an eigenvector. Of course, 2, 2 was and 3, 3 was as well, but they're all part of the same family in the form of something here and the same thing here. Now this was mapped to itself, meaning the lambda for that one was just 1. So the eigenvalue for the eigenvector 1, 1 was 1. This one got multiplied by -1, so the lambda value here was -1. If we go back to this example here, we can say that for this matrix, 1 minus 1 was an eigenvector. We can call that E1, 1 minus 1, and it got mapped to -3, 3. So its corresponding eigenvalue was lambda equals -3, because it just got scaled by -3. There was another eigenvector, let's call that E2. It was -5, 1, and its corresponding eigenvalue was 1, because it didn't change at all. Okay, so that's the intuition about what an eigenvalue and an eigenvector is. The big question is, how do we find them? And I'm going to show you that in the next video, so see you there.